All right, we're back. We're going to be on page 113, but we're talking about the law of cosines, and we just derived the law of cosines using some algebraic tricks, which means it's almost certainly not the original way that we came up with it. Well, actually, I don't know. Yeah, it's probably not. There's probably some geometric thing or something. I don't know. I'm not big on historical proofs. I just like proofs that work, or derivations that work. So we came up with the derivation. We know that if we start with side A here, we're going to end with angle A here. If we start with side C, we will end with angle C. If we start with B, we will end with angle B. Then the order of the other stuff doesn't really matter. You could switch them. Doesn't make a difference. Just got to remember there's a minus sign here, really. Because the cosine of pi over 2, or the cosine of 90 degrees, is 0, that's why this is essentially the same as the Pythagorean theorem, right? So let's say if, let's use the highlighted one. If A is 90 degrees, cosine of A is 0. Therefore, we would just get A squared equals B squared plus C squared. So Pythagorean theorem is a particular case. It's a very specific case of this, which is pretty cool to know, I think. And then a way that you can think about it, if you don't want to think about, like, you know, all the letters, I guess, is if you draw the picture, super good triangle right there. What we have is, let's see, how many colors do I need? So we have opposite. And then we have one adjacent side. We have a second adjacent side. And then the angle, I guess I'll make the same color there, right? So the included angle, and then adjacent 1 and adjacent 2. All right, so it's the side opposite the angle squared is adjacent side squared minus 2, adjacent, and then cosine of the angle. That's how I basically remember it. Like, it doesn't really matter what the letters are. You just kind of like say that in your head. It's like, oh, we have this. So it's going to be like this squared plus this squared minus 2 times this, cosine of the angle between them. So you can use it if you are missing a side. It's like essentially set up for that. Like, that's what it's designed for. So like if you knew this angle and you knew these two sides, you just straight up use it. Number one mistake that I see people make is they forget to take the square root at the end because it's the opposite side squared. If, on the other hand, you knew all 3 sides, you can still just use this. So I don't have it memorized in a specific way that will solve for the side. What I do instead is I start here, and in my head, I just solve, right? And I don't really care that I'm going to divide by a negative, which I'm going to end up doing. So I'll do c squared, and then it'll be minus a squared minus b squared, and then divide by negative 2ab, and that gives me cosine of c, and then I do the inverse cosine. So I end up here. So I've subtracted a squared, subtracted b squared, I divided by negative 2ab, which is why this is here, and then I have to do the inverse cosine. Now, inverse cosine is doing you a huge favor, because if you remember, inverse cosine only uses weird direction to draw that. This is the unit circle picture for cosine inverse. It's quadrants 1 and 2, right? Everything's positive here, sine is positive here. So if you find yourself doing the inverse cosine of a positive, you are guaranteed to get an acute angle. If you find yourself doing the inverse cosine of a negative, you are guaranteed to be working with an obtuse angle, an angle between 90 and 180. So there's nothing ambiguous, right? The ambiguity for the law of sines comes from the fact that in quadrants 1 and 2, sine is positive. So you don't actually know, without really thinking it through, should you have the acute angle or should you have the obtuse angle? No way to really know. Law of cosines, no way to really have to think about it, because inverse cosine is going to do the work for you. The problem is, if you use the law of cosines once, this isn't actually a problem. The method is, if you use the law of cosines once, use it twice so that you don't accidentally create the ambiguous case of the law of sines. Like, you don't want to do that. But the law of cosines, if you use it once to find an angle, just use it again. And it's plenty easy. On the Inspire, there are very few things that you actually need to change. So if you use it once, use it twice. if you're only going to use it once, always use it to find the biggest angle, which I will never do. But that's what you should do, because the biggest angle is either acute or it's obtuse, and the law of cosines won't be fooled by that. So it's the biggest angle is opposite the biggest side. So if you're only going to use it once, use it to find the biggest angle. But really just use it twice. Like it's so simple to do. Like, why would you not do it? In fact, I frequently will use it 3 times, because then you kind of like know if all your angles are going to add up to 180 or not, rather than doing like the 180 minus, where it's like, if you got one wrong, you're guaranteeing that you get another one wrong, whatever. So anyway, if you use it once, use it twice. Super good advice, I think. So we did cover this question. It says, why does the law of cosines never give the wrong angle that the law of sines might sometimes give you? And it's because cosine inverse, I'm going to say, is from quadrant 1 and quadrant 2 of the unit circle. And so you can't get fooled, because it's going to give you the right angle. So I don't know if that's a sufficient thing, really. But anyway, I'm going to end this here. I'm going to come back in the next one and just do some law of cosine problems, hopefully. And hopefully I will see you there. So looking forward to it.